I hope you have some energy so I can take everything out of you. So my name is Charalampos, you can just call me Babis, and we will have a quite heavy talk about isolation. So we'll be prepared. So a few things about us at first. We are a small company that doing research in the area of virtualization systems. We are involved in various commercial and research projects, and we are actively involved in various open source communities. And mostly we focus on three aspects: hypervisors and container runtimes, operating systems, kernel stuff, hardware acceleration, and lately also about cloud native and IoT. So today we'll talk a bit about isolation, as you might have guessed from the talk. And we will talk a bit about some popular sandboxing container runtimes like gVisor, Kata Containers. We'll talk about something exotic like unikernels, URNC, which is a new approach in sandboxing container runtimes. We'll have a small evaluation about all of them, and an interactive demo at the end, hopefully. So, at first, I guess everyone here is familiar with what exactly container is. So I don't have to talk a lot about it. But what I want to talk about is isolation. And when we run a container, the main thing that happens is that we actually run a process. But besides of the normal classic process isolation mechanisms that we use, like capabilities and user management, we also use some more extensive ones that come usually from the Linux kernel, like namespaces, cgroups, seccomp filters, and stuff like that. But in all the cases, we share the same kernel. And that's where the problem begins when we are in a multi-tenant environment. Because a container can be malicious. It can be malicious for various reasons. From a user who is malicious, from us or the AI who wrote the application. And the code is not well written, so it has a lot of bugs, and malicious users can exploit these bugs and try to gain more control over the container and the rest of the system. The container runtime might be buggy. I don't know if you have heard, but there have been quite a lot of security vulnerabilities found in runc, the main container runtime that was used from Docker. More and more security vulnerabilities are happening, and that's normal, like in every kind of software. The same happens with the Linux kernel, as you can guess. A huge project, it has a lot of problems as well. And that's where the problem begins, because if the user tries to attack our system, and this is the host, we're just having this on a bare metal, just running in a machine. If they manage to gain access to the container, one container, then they can slowly dig in, get access to the container runtime, get access to their kernel, get access to other containers running in the same host, and who knows where they're gonna stop. So the solution here is to, when we are talking about more sensitive workloads and more sensitive environments, like multi-tenant environments, we need to have some more stronger isolation enforcement. And that comes with sandboxing containers. And the idea here is to wrap the container in a sandbox where we don't allow the container to directly communicate with the kernel. Instead, it has to use an intermediate layer to do that. And usually we have two mechanisms for that. The one is software-based and the other one is hardware-assisted, usually virtual machines. So at first we'll talk about the software-based sandbox. The most popular one is gVisor, of course. And the idea here is that we, inside the container that we spawn, we have a sandbox, a software sandbox, where the application is running. The difference between runc is that except of the container, we have also the sandbox. So let's see how gVisor works. gVisor, what it does, it's spawn our application inside a sandbox which is created from Sentry. Sentry is an application kernel, and it's kind of tries to replicate what Linux does. So the application communicates with Sentry and doesn't communicate directly with a host kernel. Sentry does that by intercepting the system call. So every system call that the application does, it gets redirected to the Sentry, and then we have another component which is called gopher, and this component communicates with Sentry to handle any I/O and any other things that the application kernel cannot do. So In order to set up gVisor in Kubernetes, that's pretty straightforward. We have to add the gVisor component in every single node that we want to use it. This is pretty easy because gVisor is a single binary and has everything bundled together. Of course, we have to configure containerd in order to add the configuration for runNC, the new container runtime. We have to add the runtime class in Kubernetes. And at last, we can simply deploy our application or service just specifying the runtime class. Normal things. So let's see how does it look in a Kubernetes setup. So when we create a new container and selecting gVisor as our container runtime, what happens is that gVisor will first create the pod, will create the normal container. It will create a new software sandbox inside there. As I said, it will spawn Gopher and Sentry inside there, and of course any other sidecar containers will communicate with these two components. And then it will spawn the application that runs inside this sandbox. So that's how gVisor works. The next case of sandboxing is virtual machines. And we're not going to talk about virtual machines spawning a VM and then running a Kubernetes node inside there. We'll do it in a more cloud-native way where we spawn the container and we have a container runtime to manage the virtual machine for us. And that's what Kata Containers do. So Kata Containers, instead of spawning the container in the host, they spawn a VM, and inside this VM, they spawn the container that contains our application. Let's take a closer look. So Kata Containers, in contrast with gVisor, they use strong VM-based isolation. They use Firecracker, Kemu, they can use Rust, any other kind of Rust VMM variations that exist, and also other kind of hypervisors. And the idea here is pretty straightforward. We spawn the container inside the VM, so Kata has another component running inside the VM that actually does the necessary stuff to spawn the container. And the container is completely restrained because it's running inside the VM. It can only communicate with the host only through the hypervisor. This is the best we can do in terms of isolation. And of course, in order to make this work, Kata Containers come with their own guest kernel. They come with some specific components that they have to be present inside the guest, like the Kata agent, who is responsible to spawn the container inside the VM. We will see that later in the Kubernetes slide. So, to set it up in Kubernetes, it's again an easier process, but the difference here is that because Kata has so many components, the monitor process, the kernel that we have, the initrd, all this, the rootfs, all these kind of components, it's quite difficult to add it in every node. But they provide a tool for us called Kata Deploy, and they can make this installation process very easy. It adds all these binaries that I just said. It also adds Kata Containers in the containerd configuration, and also add it as a runtime class in our Kubernetes cluster. So in order to spawn a pod, we can simply specify the runtime class and just use Kata Containers, and that's easy, again. Okay, so as you can see, with Kata, the model is different. So when we select it to spawn a container for us through Kubernetes, Kata at first will create a new VM. This VM will have a very small Linux kernel running inside. It's not a distro. It's a custom small kernel with a custom rootfs that contains a Kata agent. The Kata agent is, you can think about this as a container runtime running inside the VM, and it communicates with Kata over gRPC, so with the Kata runtime running on the host. So whenever we want to spawn a container, we have to communicate from the Kata runtime running on the host. We send the respective gRPC message to the VM running inside, and Kata agent spawns the respective, does a respective operation. And at the end, we spawn, of course, after we spawn all the sidecar containers, then we spawn the actual user container. That's also how Kata works. So as you can see, both gVisor and Kata add a lot of additional layers between, compared to what would, for example, a normal container runtime like runc would do. And so let's see how this would work, for example, in a serverless scenario. So in order to do that, we created a very dummy micro benchmark, and we just wanted to measure the startup time for a serverless function. And we created a very, 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 very simple function. It's an HTTP reply, which doesn't do any computation or something. It just receives the HTTP request and just does reply. It's written in C in order to be as fast as possible because we don't care about anything else. We just want to measure the startup latency. And we invoke it from the same node, so the numbers are taken from the same node in order to just avoid any kind of network issues. And we measure the round trip time. This evaluation is taken in a small NUC running in a small single node cluster. And here are the specs of the NUC device. So here are the results. As you can see, runc is of course faster. gVisor and Kata has two variations with Firecracker and Kemu. You can see that both gVisor and Kata have almost double startup latency compared to runc, and that's quite bad. So the question is, can we make that better? Can we reduce this kind of overhead, specifically for the startup latency? And yeah, so of course, optimization comes with specialization. And we can do that by minimizing what we want to execute. And taking a closer look of what exactly we are running when we spawn a container, we see that we have all this kind of stack that we have to execute. But actually, what an application really needs in order to execute in a cloud-native scenario, when we have small components running in a cluster, are very, very small parts of its. For example, if we want to have an HTTP server, we don't need, for example, if we have this previous example of an static HTTP server, we don't need a lot of stuff. We don't need a lot of stuff from the kernel, we don't need a lot of stuff from the libraries, we don't need any of these kind of things. So we can only cherry pick what we need. And that's where the unikernels come. So with the unikernels, we can cherry pick what exactly the application needs. And we can combine everything together, and we can simply have this kind of blob, a small binary that we can use. So, how many of you have heard of unikernels before? Oh, wow, that was surprising. Okay, so a unikernel is a specialized single address space image that we can spawn around different kind of virtual machine monitors, or sometimes even in bare metal. And it's usually constructed from library operating systems, which means that we take a kernel, we make it a library, and we can cherry pick different components. The benefits of such setup is that we can have very, very fast boot times, extremely fast compared to any other kind of OS that we have out there right now. Of course, smaller memory footprint because we don't have all the noise from all other services that run. There are much, much reduced attack surface and really, really true isolation since we are running a VM actually. So every time that we talk about unikernels, these come in mind, and a lot of people ask, okay, good, they sound good, how can we manage them, like in a Kubernetes cluster? And that's where uRunc comes. So uRunc tries to be the runc of unikernels plus. Plus means that we can also boot more things than unikernels. It's a CNCF sandbox, newly CNCF sandbox project. It's a CRI compatible runtime written from scratch. That was a bad idea, but it worked. It supports both software-based and hardware-assisted sandboxes, and it's highly extensible. We can easily add new guests, we can easily add new unikernels, any kind of guest, and we can also add any kind of monitors without any modifications. So let's take a closer look of the difference between uRunc and other kind of container runtimes and sandboxing technologies. As you can see, runc resembles a bit of the gVisor technology, but it tries to merge gVisor and Kata. So we can spawn, we create a container, and inside this container we create the monitor process, which can be either a virtual machine monitor process or a software-based monitor process. So, the idea in URNC is that the application is coupled inside the guest that we want to execute. This can be either a unikernel or even a Linux VM if we want to execute a normal container. We can spawn the app directly. We spawn the app directly inside the monitor, so think about it as the init process being your init inside your container. And it treats the monitor process as the container process. So we can manage the container and the process running inside the container through the monitor. We have one VM per container, and this allows us to have a fine-grained isolation even inside the pods. And we will see why this is useful. So to set up URNC in Kubernetes, similarly with Kata deploy, we have URNC deploy, which makes the installation very easy. It will install in our nodes all the monitors that we need. The difference here is that we don't need any kind of custom kernel. We don't need any custom rootfs. We just need the monitors. And the reason is that the application is the actual kernel that we will execute. And of course, URNC deploy will add URNC in containerd configuration as a runtime class in Kubernetes, and we can easily deploy. For example, here we have an example of running an Nginx over Linux and QEMU. So let's see how URNC works in Kubernetes. So the idea here is that we treat any kind of sidecar containers, any kind of containers that are part of the let's say, of the system stack. So this could, a better example would be Knative. So Knative, if you're familiar with, comes with kubeproxy. Kubeproxy is a sidecar container running inside the pod along with the user function. So the kubeproxy container, or the post container, or any kind of sidecar container that is part of the stack will run as a normal container. But the user container will be treated differently, and that's where URNC comes. The user container will be, URNC will create a container where inside this container it will create the VM or for example, a sandbox monitor to spawn the application inside this sandboxed environment. So everything is so we can have inside the pod we can have even different kind of isolation layers. So the current state of URNC, as guests, we can support different kind of unikernel frameworks that exist out there, like Rampran, which is based on NetBSD, Unicraft, which is written from scratch and it provides Linux binary compatibility, Mirage.os, which is written in OCaml and supports only OCaml applications, Muse, which is a WASM unikernel, and of course Linux. As monitors, we have support for QEMU and Firecracker, and also for Solo5. Solo5 is a specialized monitor process that provides two kinds of execution modes, the one that uses KVM and one that uses a sandbox with closely resembling gVisor, but only allowing 5 system calls. These 5 system calls are the normal system calls that just do I/O, like network and block, that's all, nothing else. So the use cases we can have for URNC are for any kind of short-lived microservices or any kind of services that we care about isolation and fast startup, like serverless, for example. Any kind of untrusted workloads that we want to isolate and we are sensitive about it. And of course, for providing isolation in resource-constrained environments like in the AIDS. So let's take a look on how URNC behaves in serverless in the benchmarks that we had before. So as you can see, we have different kind of URNC instances running. So here, I don't know if you see my mouse, but here we have the Linux running on top of Firecracker and QEMU. You can see that in the case of Linux and Firecracker, we have an overhead of around 24%. In general, in Linux, we see that it's around 30% of overhead, but still it's 1/3 of the overhead we would have with Kata containers. And if we even go for unikernels like Solo 5 that either using KVM or not using KVM, we can have like around 16 to 17% of overhead. So we have time, so we can play a bit. So I will need your cooperation with that. The idea here is that we have in the Nook that we did the experiment, we also have some small services running. These are just static HTML, static HTTP server. So I will show you some QR codes that they are going to this HTTP server. And in the meantime, I will also have we will also see the pods running, and we will also see the processes that run in the machine. Okay, so I just need a volunteer that will try to invoke this one. That is gVisor. I just need one person. Okay, so we can see here that we have some instances running, and we can see here that you can see run and see sandbox. This is the gVisor running here, and this is you can see the pod that has been running and it's trying to terminate now because it's just scaling down to 0. And here we have the process of the run and see running. Let's try to do the same with Kata. And we will do it now with Kata and Kemu. So the idea here is that we will see a lot of Kemu processes running. So here you can see we have the Kemu running. And this is, you can see it takes some time to start, but you can see all the processes running here. And now we can do the same with URNC. So now with Kata, we were running inside the Kemu process that was spawned automatically, and the container was running inside Kemu over Linux. And we'll do the same with URNC and again with Linux. Okay, and you can see that it started we have some errors in Kata. Okay, yeah, we know about these errors. So, and yeah, I think, yes, this is the Kemu that runs that spawned from URNC. You can see it's running over just 250 megabytes. And it's just, it's not visible here, but if you see the init process is nothing, there is nothing running inside the container except of the HTTP server, this static HTTP server that you see that is serving, nothing else. So the init is this kind of server directly running without any external processes. So if you want to play more, there are more functions that you can invoke with different kind of combinations like unicraft, ramprun, other kind of unikernels that they all do the same thing. It's just this kind of silly HTTP echo server. We're in the process to improve the demo to showcase the difference in the time, so you can really see the difference on spawning. If you have any idea, feel free to let us know about it. So, okay, so to sum up, containers are great. We all love them, and we know that they're here and they will stay for a long time. But if we care about isolation, if we have sensitive workloads and sensitive environments, they are not the best option for us. And we need to provide some kind of sandbox execution to have stronger isolation. But this kind of sandbox might come with some kind of overheads, even in startup, even in IO, or in other kind of cases. And with URNC, we try to reduce this kind of overhead. We try to make it as small as possible, but still provide an isolated environment. And you can find the repository, of course, in GitHub. You can find the website and the documentation of URNC at urnc.io. We will be happy to have any comment from you in the CNCF Slack channel, workspace, and then you can find the URNC channel. So please get in touch with us. If you have any ideas of whatever you want to try, if you encounter any issues, something that you want to add, something that you don't like. And you can also find in the repo and in our website some more communication channels. So that's all from me. If we still have 4 minutes or more, so let me know if you have any questions.
Thanks for the nice talk. Now, it was mainly about the security of the runtimes, but the unikernels have one disadvantage that you need to prepare them beforehand, right? And how much is the overhead to build it?
That's a true pain. But I would compare it like currently there has been quite a lot of work with unikernels that especially in the area of Unicraft, they try to simplify the process of creating the unikernels and make it smooth. And because of we identify this as a problem, we also have a tool called Bunny. So Bunny is trying to create the unikernel for you. So the idea is that it will take your container, it will transform it to unikernels. It will try, in the long term, it will identify all the dependencies automatically, and it will build it for you. Right now, it's dummy. It just jumps. No, I'm kidding. It just does very small things for URNC, but yeah, in the long term, we are working on making it much easier for the people. Like with Bunny, you can just do a Docker build. It's a build kit front end, so it integrates smoothly with Docker. So you can do a just Docker build, and it will build a unikernel for you, ready to deploy it in URNC. But maybe in some other time, I will have some time to talk more about Bunny when it's also more mature. Okay, we have one more question.
You mentioned that there's a sidecar container running next to the URNC managed VM. I did not quite get why this needs to be the case.
So you're referring in this case, right?
Yeah, yeah, exactly.
Okay, so this has to do with we had, for example, a case that we were researching about the security issues that there might be, for example, in the case of Knative, where a malicious container takes control over the pod. We are not, actually we are not Knative experts. We don't know a lot of things about it. But if the malicious container takes control over the pod, it can take control over the kubeproxy, and there might be some cases that it can communicate with Knative, and it can ask, for example, to replicate it itself. It can ask to do any kind of things. It can stall for example, the pipeline. It can do a lot of things, and the idea is that we want to have separated any kind of sidecar container that is our component, our code in a cluster, in a setup. This is our code. It might have some secrets inside. It might have different kind of things. Normally, people, hopefully, they don't do that, but you don't want, there are some cases that you don't want a malicious container to take control of other kind of containers that even run in the same pod.
So, if I may ask a follow-up, but how do you designate the containers to a runtime then?
Yeah, we use annotations, runtime annotations. So URNC has some specific annotations that we pass through containerd through the emads, and URNC can recognize that this is a specific container that I need to spawn in a different way, and all the rest are handled normally like runc or any other kind of container runtime.
Thanks.
Okay, so thank you again for coming to the talk, and have a nice evening.